All right, we're just going to look at graphing trig functions, which of course we have seen before. The only difference is we'll use radians instead of degrees. So we'll start with the sine curve, our basic sine curve. We know it goes between -1 and 1, so I'll mark that on the y-axis. I like to mark in the boundary values, so now I'm marking them off instead of every 90 degrees, it's every pi on 2 radians, although I'm only labelling them multiples of pi, you'll notice. And our sine curve, it starts at the origin, and then we know it goes up to 1, and then it goes back down, and we get that alternating pattern up and down, and so on. And we draw a nice smooth curve between them, and there's y equals sine x. So what do we know? We know its domain is all real x. The range is in between -1 and 1. It's an odd function. It has rotational symmetry about the origin, which of course means sine of negative x is equal to the negative sine of x, so we can use that fact. Now there's a couple of terms which I don't know that we really looked at before, but let's just go over them anyway. Period. So a period is just a regular interval. How long does it take for this pattern to reoccur? Now it can be deceptive if you look at the x-intercepts, because it looks like, oh, every pi I'm back. So I guess what you're looking for is not only is it at the same point, but it's travelling in the same direction as well. Now I can't use the origins going up and then pi's going down. That's no good. So I've labelled the 2 peaks there, so that would be our period. How do we work it out? Well, for the sine curve, yes, it is every 2 pi. And the amplitude is how far it goes up and down the axis, so the amplitude is 1. All right, let's have a look at cosine then. So same deal, let's label the y-axis, -1, 1, mark off all the boundary values. Now our cosine curve starts up at the top, so we'll plot that one in. And then that one goes down, and again we get that up and down pattern as we go along. Nice smooth curve. Don't put arrows on the end of this curve, because that implies it's going to just keep travelling in that direction. And of course the cosine curve doesn't. It will then turn and go back up again and so on. So we don't put arrows on the end of the cosine curve, or the sine curve for that matter, when we're talking about a restricted domain. Okay, domain though for the actual curve is all real x. Range is also -1 to 1. Makes sense because the sine curve and the cosine curve, same curve. It's just a horizontal shift. But this one becomes an even function because we have that reflectional symmetry, which means we could use the cosine of negative x is equal to the cosine of x. Period is also 2 pi. Again, same curve, got to have the same period. And the amplitude is also 1. They are complementary ratios, so that's what I was saying. It's actually a shift. The cosine curve is the sine curve. That means our curve has reflected sine x in the y-axis and then shifted it right pi on 2. So they are the same curve. Let's draw our tangent curve. That's the different one, of course. I don't bother marking anything on the y-axis. I don't really need it unless I'm using the graph for something. But I will mark off the boundary values. We know this one starts at the origin, but then we get an asymptote, and that pattern repeats. Our tan curve does that. It bends towards the asymptote, as all curves do. Why do I know it's there? Because the first quadrant between 0 and pi on 2, so it must be positive. To the left, that would be our 4th quadrant, tan's negative. So I know it goes like that. It inflects at the origin. When you draw this, that should be at 45 degrees. At that point. That should be 45 degrees. And that curve repeats in between all those asymptotes. Well, the domain, how do you write this one? You've got all these exclusions. So I write it using a generalisation. It's all real x, except, so I'm saying, well, I've got my first asymptote at pi on 2 here, but then every pi, there's another one before and below. So I'll say pi times k, where k is some integer. So every multiple of pi before and after will get an asymptote. The range is all real y. There are no breaks going vertically. We have an odd function because we've got the rotational symmetry there, which means we could use tan of negative x is equal to the negative of tan of x. Now the period for the tan curve is different because this one it's only pi. It repeats. Amplitude has no meaning when we're talking about tan, because it doesn't go up and down like the other one. Right, let's do a reciprocal one. Let's do cosecants. Cosecant is, of course, the reciprocal of sine. So I'll draw in the same boundary values and the 1 and the -1, and I'll just dot in the sine curve. So the basic curve is the sine curve. I've dotted it in because, remember, this is not actually part of the graph. And same as we do with asymptotes and things like that, we usually dot those in to say this is not actually a piece of the graph itself. We're turning it upside down. So what did we say when we turn things upside down? Well, x-intercepts become asymptotes. So every one of those x-intercepts is now a vertical asymptote. When you turn one upside down, you're going to get one. So the peaks and the trough there of all of those are still going to be there, those particular points. But we also said anything less than 1 becomes above 1. The sine's not going to change. So instead of, well, let's start at the first one over here. Instead of it being concave down, it's now concave up. This one, instead of being concave up, it's now concave down. You get a whole series of U shapes between the asymptotes on that one. So 11J, let's do some drawing. I know we love curve sketching.